Hey everyone, today we're looking at P.4, Day 2. We have a variety of topics. We'll talk about finding X and Y intercepts. Again, we've seen this before. And then solving quadratics, and there's a variety of methods how we might solve these types of equations. Whether it's by factoring or quadratic formula, we'll overview the methods we're looking at today. So let's start off with the intercepts. All right, so when we're talking about an intercept, we know that it's going to be a point that is on the x-axis for an x-intercept, and it will be on the y-axis for a y-intercept. So here's a little diagram to represent that. Here's my line crossing both of the axes, but we're just focusing on this one here for the x-intercept. So that means you have some value of the x-coordinate, and your y is 0 exactly, because you're not above, you're not below the x-intercept, you're exactly on it. So your height is 0. So when we're solving these equations, we'll set the y-coordinate equal to 0 so that we can solve for x. So that's for the x-intercept. For the y-intercept, now we're talking about a point that is not to the left or right of the y-axis, but on the y-axis itself. So that means for us that we have a point here where the x-coordinate is set to 0 because it's not to the left or not to the right. And when we plug in 0 for the x, we can then solve for y. So we'll do that down here in example number 1 in just a moment. Here are a few pictures of how we might have a variety of different intercepts. In these 3 cases, we're just looking at a few instances. If we were to try and come up with a sketch of a graph that had 3 x-intercepts, for example, well then that means our graph has to go up and down a few times so it can cross over the x-axis in more than one place. So something like this perhaps might work, where you have 1, 2, 3 solution points. That means you have 3 x-intercepts, and you can see you have exactly 1 y-intercept in a case like that. If we're looking at a graph that has no x-intercepts, that means it cannot cross the x-axis at all. So there's a couple of possibilities. You could have a horizontal line, for example. So y equals -5 would be a horizontal line that crosses the y-axis at -5. You could also have a parabola. That's another classic example where, because it opens upwards, it will never come back down to cross the x-axis at all. So here's your vertex. And so that vertex is at a place not on the x-axis but above it, and it opens upwards. If we were to reflect this upside down, you could even have a parabola opening downwards, and then we would have exactly 1 y-intercept, and it does not cross the x-axis. And in this case, if we had no intercepts at all, that's a more specialized case. It would be something like a circle, where the center and the radius are of values that wouldn't cross either axis. So when we're solving for the x-intercept, we're trying to figure out what are these solution points. How many times does it touch that x-axis? So if we get an answer, we know it crosses the x-axis. But in a case like this, we wouldn't get an answer. We would come out with an imaginary solution, which means that the graph never crosses the x-axis. Here's just one example. Let's find the intercepts of this equation, y equals 2x times root x plus 6. Let's start by finding our x-intercepts, and to do that we want to set y equal to 0. So 0 equals 2 times x times the root x plus 6. So that might look a little scary with the radical in there, but remember that if you have factors, right, factors are things that are multiplied together, you can split up those factors so each factor is set equal to 0. So you have these little mini equations to solve now instead. So x equals 0 means that I have an x-coordinate of 0 and a y-coordinate of 0. So that's the ordered pair. So at the origin is where my graph crosses the x-axis. For the other, let's square both sides. So we have x plus 6 equals 0, and then move the 6 to the other side. So that tells me that at -6, 0, that's the other coordinate point. So this crosses the x-axis at 2 places. Where does it cross the y-axis? Let's find y. To do that, we'll set x equal to 0. So y equals 2 times 0 times the radical 0 plus 6. So here, because we have a factor and because we're multiplying everything by 0, well, then the answer is just 0. So that tells me when x is 0, y is 0. So these points are really the same, and that means that is the only place where it's crossing the y-axis as well. So this fits in our chapter here, or in our section, because we're talking about solving equations, and you can see we're creating these equations by taking a value, set it to equal to 0, and then solving it from there. So let's look at some other methods for solving equations, and we're focusing on quadratics specifically. Here are a variety of factoring patterns. We're going to be looking at solving by factoring. We're going to look at the square root principle, what we call extracting the roots today, and then we'll also look at the quadratic formula today. We'll do completing the square in the next lesson. So here for just review are some of the factoring patterns. If you have a difference of perfect squares, that factors into a plus b times a minus b. This is also a special factoring pattern. You have a trinomial, but the first term is a perfect square, the last term is a perfect square. And in a case like this, we can then create identical binomials and write that up as a binomial squared. Now, if this was a minus sign in front of that middle term, then all of these would be minus signs instead. So often we write this as plus or minus in each of those patterns. We don't always encounter problems where we have to factor the sum of perfect cubes or the difference of perfect cubes, but those are patterns that we've seen before, so here they are for reference. And we also have this factoring by grouping, which is not a particular pattern, but it is a particular system or sequence of steps where we're going to group these into pairs. So let's just do this example now, then we'll go to the bottom of the page and look at a couple other factoring examples. So, for example, x cubed minus x squared plus 4x minus 4. We'll pair up the first two, we'll pair up the last two, and see what is the greatest common factor of each pair. We can factor out an x squared from the first pair, leaving us with an x minus 1 on the inside. From the second pair, we can factor out a positive 4, leaving us with an x minus 1 on the inside. And this is your check. You should make sure you have identical binomials at this point. If you don't, that means you cannot factor in this method, or we have to make a slight change. But we do have an identical x minus 1, so that's the common binomial that we are factoring out from the front, leaving us with the x squared. And we're factoring that out from the back, leaving us with a positive 4. So there's an example of factoring by grouping. Let's look at a couple more examples down here. So in example 1, part A, we have 6x squared equals 3x. This isn't any of the patterns we've seen so far. If we want to remove a common factor, that means we need all the terms on the same side, so we can identify what the common factor is. Notice we only have 2 terms, and when you only have 2 terms, you just have to remove the common factor. So 3x should do the trick. 3 times 2 will give us the 6, so we want a 2 in front of that x. And 3x times a minus 1 should give us that negative 3x. Once again, we have factors, and as long as you have factors, you can separate those factors. And of course, as long as you have everything equal to 0, it doesn't work if you have any other number. It has to be a 0. And we get our 2 solutions here. So this method that we've seen right here, we've done that a few times. It has this official name. That's the name of it, the zero product property. And so what that is saying is that you have to have a 0, right? So it has to be set equal to 0. And you have to have a product. That means you have to be multiplying, and we are. So we call those factors. So if you are multiplying these factors and the equation is set equal to 0, then each factor can be set equal to 0 and solve them independently of each other. That's what we're doing in these problems. Here, let's solve this quadratic by factoring 9x squared minus 6x plus 1. Now, there is a special pattern to this, so we can factor it really fast. However, I'm actually going to do it a slower method, and that's because sometimes you don't see the pattern, or sometimes you have a problem where there is no pattern. And so I want to remind you of this method we've learned earlier. We call this X and box method. So, yeah, we can actually factor this super fast, but let's just pretend we don't see the pattern and use this as a way of reviewing this X and box method. Here's your A, here's your B, here's your C. In the top of the x, we're going to multiply A times C, and we'll put the value of B at the bottom. So 9 times 1 at the top, and negative 6 on the bottom. Next, we want to think of two terms that will be multiplied up to the positive 9, but when added, we'll add down to that negative 6. So we need numbers that are negatives here to add to the negative 6, and they also both have to be positive, so they multiply to a positive 9. What we're doing is we're throwing out that middle term and replacing it with these two numbers, the negative 3. So that means they have to have the same variable of x, because they are replacing that middle term, which has an x. The 9x squared goes in the top left corner of the box, and the constant term goes in the bottom right. The other two cells of the grid are both the same, so we fill them in with the negative 3x's here. What we're doing is we're really turning a trinomial into 4 terms, and we're really factoring by grouping. So let's remove the common factor out of the top two, so we can factor out a 3x. So 3x times something at the top should give me this 9x squared. 3x on the left times something at the top should give you the negative 3x, that's a minus 1. Checking the leftmost column, something on the left times the 3x at the top should give me that answer of negative 3x, which is a minus 1. And now we check our answer. Negative 1 times negative 1 should multiply to that positive 1 inside, and they do. So these are the answers. The factoring pattern gives you the exact same result, 3x minus 1. So that tells us, yeah, we could have used that special pattern up here. This is a perfect square trinomial with a minus sign in the middle, so we could have factored it like so. Don't forget, set that equal to 0 because we're still solving it. Separate each of your factors so they each equal 0. And, curiously, we get duplicate answers. Oop, that's a 1/3. So 1/3 and 1/3. So when you have duplicate answers like this, we call that a multiplicity. So we could format our answers by saying x equals 1/3 with a multiplicity of 2, meaning there are 2 copies of that answer. So that's one way you can format the answer. We'll do that more in future sections. So that's the solving a quadratic by the factoring method. Some of our quadratics can be solved using this square root principle, or the book will call it extract the roots. Now there is a very special pattern. You have to have an x squared on one side, and you have to have a single number on the other side. And then you take the square root of both sides, and don't forget your plus or minus. Another way to represent this is you could have a binomial squared. But again, the pattern is you have to have a single number on the right-hand side. So if you don't have a single number on the right-hand side, you cannot use this method. All right, let's take a look at some examples at the bottom of the page. Here is example 2, part A. We have 4x squared equals 12. So I do have a single number on the right-hand side, and I have an x squared on the left, but that x squared is not isolated yet. Let's divide both sides by 4 so that we can get that x squared by itself. Now we have the pattern. X squared on the left, a single number on the right. Take the square root of both sides. Don't forget the plus or minus. And you get x equals plus or minus root 3. Right? 2 answers. Here in part B, this is also the pattern. Notice you have a single binomial squared. There's no other multiplier. Otherwise, you'd have to get rid of it. You have a single number on the right. So again, extract the roots. X minus 2 on the left equals plus or minus the root 5 on the right. Add 2 to both sides to get the variable by itself. So positive 2 plus or minus root 5. Notice, again, you get 2 answers. So you want to compare these 2 problems that we just did, the pattern of them, with this next example, because there's something different here. Here in part C, you have a binomial squared on the left, and you have a binomial squared on the right. That's not the pattern, right? The pattern is you must have a single number so that you can take the square root of that and get that plus or minus. And I don't have a single number here. So this one is different. It's deceptive because it looks like you should be able to take the square root of both sides just because you have the power of 2, but you can't. The only way to solve this is to FOIL both sides. That means you have an x minus 2 times x minus 2 on the left, and x minus 3 times x minus 3 on the right. So let's FOIL that out. We get x squared minus 4x plus 4. So I FOILed it out and I combined the like terms to get that middle term. On the right-hand side, again, x squared minus 6x plus 9 is the result. And when you try to combine your like terms by moving the x squareds to the other side, notice that they drop out. So notice we don't even have a power of 2. It looks like a quadratic, but it's not. It's a linear equation here. So let's add 6x to both sides. So we end up with positive 2x plus 4 equals 9. Subtract the 4 from both sides. Notice we get one answer. There is no plus or minus like we did here. So that's why the pattern is different. So it looks like you should take the square root of both sides, but you cannot. So that is the square root principle, extracting the roots. So lastly, our topic for today is the quadratic formula. There's the formula again for your reference. And let's go to the next page so that we can take a look at our two examples there. So on the next page, we're looking at example 3. We're solving these quadratics with the quadratic formula. All right, so first bring all of the terms to the same side. X squared plus 3x minus 9 equals 0. We have our a, which is the 1, the b, which is the 3, and the c, which is the negative 9. So x equals negative b, which is the 3, plus or minus square root of b squared, 3 squared, minus 4 times the value of a times the value of c, all divided by 2 times a, so 2 times 1. So order of operations says we have to do what's here inside these parentheses, right? That radical is a grouping symbol. So we have a 3 squared, which gives us a 9. And watch out, this is where I see the most mistakes. When we're doing this multiplication, notice that you're multiplying a negative with a negative. So negative 4 times negative 9 gives us a positive 36. That results in a 45. So negative 3 plus or minus root 45 all over 2. And then always look to see if you can find factors to simplify that radical. So we want 9 times 5. So the square root of 9 gives us 3. So it's negative 3 plus or minus 3 times the root 5 all over 2. So there's the final result. The only thing different in part B is that we have a leading coefficient that's not 1. So we have an a of 8, a b of negative 24, and a c of 18. So here we go. X equals negative 12 plus or minus the square root of, that's a 24 there, not a 12. What I'm doing here, sorry, I didn't think to write this down, and I'm realizing I need to back up a moment. All of these values are evens, so we can plug in those numbers and there will be really large numbers to work with. What I'm doing here first is I'm saying, what if we divide both sides of the equation by 2? So let me just push it up here. So we have 4x squared and negative 12x and positive 9 equals 0. So instead of using the 8 and the 24 and the 18, I'm using the 4 and the negative 12 and the 9. So I'm just doing that as a technique so that I have smaller numbers to work with. And that's why I wrote down the negative 12. I forgot to just take care of that first. But you could use those original numbers. It would still work out just fine. So there's my opposite of the value b, the negative 12, plus or minus the b squared, so negative 12 squared, minus 4 times the value of a, which is the 4, times the value of c, which is a positive 9, all over 2 times a, so again the value of a is 4. So that means we have a positive 12 plus or minus, and inside we have 12 squared, which is 144. I know it's negative, but negative squared is still a positive 144. And then negative 4 times 9, my calculator gives me, it's actually the same value, so those will cancel out here. So what we end up with is just 12 over 8, because the whole radical turned to 0. Now, keep in mind that we have this plus or minus. It's technically plus or minus 0, right? So we actually get 2 duplicate answers. So it's not just a 3/2, it's 3/2 with a multiplicity of 2. So we still get 2 answers, even though we're adding 0 and subtracting 0, so they end up being the same answer after all.